Hello everyone and welcome. I'm excited to introduce you to a fascinating problem in computer science and operations research, the traveling salesman problem. In simple terms, it involves finding the most efficient route to visit a set of cities. So, buckle up as we explore this problem and understand its complexities. Let's define the traveling salesman problem, often abbreviated as TSP. Imagine you have a list of cities, and you know the distance between each pair of cities. The goal is to find the shortest possible route that visits each city exactly once and returns to the starting city. This might sound simple, but the challenge grows rapidly as the number of cities increases. You might be wondering, where does the traveling salesman problem show up in the real world? There are many applications. One common example is optimizing delivery routes for trucks or drones, ensuring packages are delivered efficiently. It also appears in manufacturing, such as planning the drilling sequence on circuit boards or optimizing assembly lines. By solving the traveling salesman problem, businesses can save time and money. Here is where things get tricky. The complexity of the traveling salesman problem increases dramatically with the number of cities. For n cities, there are n-1 factorial, divided by 2 possible routes to evaluate. The expression n-1 factorial, divided by 2, grows exponentially. This makes finding the absolute best solution a challenge. The traveling salesman problem is a famous example of an NP-Complete problem. NP-Complete problems are problems that are both in NP and NP hard. In simple words, it means that while a solution can be quickly checked for correctness, finding the solution in the first place is very difficult. Specifically, the decision version of TSP is NP-Complete, and the optimization version is NP hard. This is why finding the optimal solution becomes incredibly hard as the number of cities increases. So, how do we tackle the traveling salesman problem given its complexity? There are several approaches. One way is brute force, where we check all possible routes to find the shortest one. However, this is only feasible for a small number of cities because its time complexity is O of n factorial, which is exponential. Another approach is to use heuristic methods like the nearest neighbor algorithm or genetic algorithms, which provide good approximate solutions in polynomial time. These methods may not guarantee the absolute best route, but they're much more practical for larger problems. Let's take a look at a simple Python code snippet that uses the brute force approach to solve the traveling salesman problem. The code generates all possible permutations of the cities and calculates the total distance for each route. It keeps track of the minimum distance found so far and the corresponding best route. While this method works, keep in mind that it's not efficient for large numbers of cities. It's useful for understanding the problem, though. The traveling salesman problem highlights the limits of computation. Due to its exponential time complexity, finding exact solutions becomes impractical beyond 20 to 30 cities. However, there is hope. Approximation algorithms and heuristics can provide near-optimal solutions in a reasonable amount of time. The traveling salesman problem demonstrates the importance of approximation algorithms in computer science because of these computational limits. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.